All right, hello STAT350 class. My name is Roshan, and my partner Noah is here too.
Hello.
And here's our final project. We're talking to talk about different random processes and analyze them. And our first one is the moving average process, which Noah will talk about right now.
Yeah, so here is the definition of the moving average process that we're discussing in the next couple of slides. We got some nice definitions up here for the expected value and the variance of these random variables inside the function. And this function is essentially just the weighted values summed together of the three instances of these random variables.
All right, and then continuing off that, we're going to be having different definitions that we're going to use throughout these two problems. We're going to find the mean function, autocovariance function, use autocorrelation function to find the power spectral density, and apply filter theorems and Fourier transform concepts from the appendixes and tables to find the problems and our answers.
All right, here is three realizations of that function in the last slide. So as you can see, they are not corresponding to each other or anything like that. They're very much random variables. But as we will be able to show in the next few slides, there are ways that we can describe this in a more understandable way. And to start off, we will use the mean function.
All right. And then continuing off that good visualization just to see how the function works and how the trends are and stuff. We have our mean function here, and it's pretty straightforward. The mean function is equal to the expected value, and we apply expected value properties and formulas to simplify our problem. And we get e to the z of n eventually times 0.8 plus 0.3 minus 0.1, which is the e of z of n, which is 1. And we have that for our mean function.
Yep, and here is that visualized. If you remember the explanation of the expected value, it is the center of mass of a random variable, and you can see how that kind of matches up with this graph. You can kind of try to imagine that these realizations are balancing along this. All right, next I will talk about the covariance function, autocovariance function. And so this is pretty similar to the last slide, just a little bit more complicated. So you expand both of these processes, and then you just break that apart. And then you end up with this big, ugly block that we simplify in this last line here. And in order to simplify that, we use these delta functions to recognize when these terms will actually come out non-zero. So k is equal to m minus n. And so if k is equal to 0, this delta function fires and we get this output. And so when k is equal to 0, that means m is equal to n, which means that this won't be 0, this won't be 0, and this won't be 0, and all the other ones will be. So we sum those up, and these two are found by similar processes. And finally, we can simplify this down a little bit further by using the variance definition we were given at the start of this problem. The variance of z of n is 4, and then you end up with the autocovariance function.
All right, thank you, Noah. And then continuing off that, finding the power spectral density is pretty straightforward. It's a Fourier transform of the autocorrelation function. And to find the autocorrelation function, we have to use the two things we found previously just to find it. So we plug in our autocovariance function, which we found, which is Noah's underlining, and we add it to 1 squared, which is our main function is 1. So we just do that, and then next we combine it together, take the Fourier transform of that entire expression, and then after doing that, we get the various properties. Oh yeah, and then from the various properties, we can look at the chart, and we can sub in the different equations and different transform functions, and we get 2.96 plus 0.84 e to the minus n plus j2 pi f minus 0.32 e to the minus n plus j4 pi f plus delta f. And that simplifies more to the bottom part, which is what we get for our answer for the PSD.
And here is a visualization of that PSD. Important thing to note is that this nice clean function is discontinuous at 0 because of that delta function, and that just bumps it up to 3.32. And we can see that this process is stationary. The mean function we found is in fact constant, and the autocovariance function can be expressed as following in terms of only m minus n.
All right, and then for this problem, we applied a filter to our moving average process, and our filter of choice was h of n is equal to 0.5 mu of n. And then transforming that to the frequency response, we get h of f is equal to 1 over 1 minus 0.5 e to the negative j 2 pi f. And if you remember carefully, y of n, the output, is equal to the h of n convoluted with x of n, and the PSD of this, sy of f, is equal to the magnitude of our frequency response squared times the original PSD that we found before.
All right, and so to expand on some of that, we're going to be finding the PSD of the output of the filter, and we'll break that into two parts. So to start, we'll find the magnitude squared of the frequency response, which, if you remember, is just the frequency response times its conjugate, which is expressed here and can really simplify down to this, and then we just tack that on to the PSD we found for the process we were given, the input to the filter.
And then here, after finding that output, we have the visualization of our power spectral density, and we have that is discontinuous at f equals 0, and that at 0, with the PSDs analyzed, we have a value of 313.3, and we see that's pretty high up compared to where our graph is on our scale. To continue, we have our random phase process. And then, yeah, go ahead.
Thanks. So we have a new random variable, which is going to be a uniform random variable from negative pi. And that's going to be the phase of this process we have down here. So that's why it's a random phase process. Here's a random variable.
All right, and then after graphing this process to visualize it, basically what we did is we took the phase part, cosine 2 pi times 300t plus theta, and we applied it where theta's different numbers in these cases. And we see we put theta 0, pi over 2, negative pi over 2. We see that negative pi over 2 is kind of shifted towards the right a little bit, pi over 2 opposite, and then 0 is in the center. You can see how all these graphs are connected together and how they all take up a similar shape, just shifted by their different theta values, of course.
All right, so for the mean function, we have this equation here. We break the expected value into the definition of an expected value, which is the integral of the random variable times the function that we are taking the expected value of. And since this is all just a constant, we can move this outside the integral, and the integral of theta from negative pi to pi is going to be 0. And another way to visualize this, we can come over here and we can see that if we move our phase, we get values that cancel each other out here. Back to the presentation.
All right, thanks, Noah. And then continuing this problem, basically, so kind of like a similar process we did before, we're going to be utilizing the autocorrelation function to find our autocovariance function. So what we have is the autocorrelation function, which is equal to autocovariance plus the mean squared. And we know that the mean for this is 0, which we found previously. And then after simplifying that, we have the autocovariance, which is the autocorrelation, apparently. Not actually, if I'm getting it. And then you have expected value of e of x times e of x of s, x of t. And then you plug in cosine 2 pi, 3 of s plus theta, and 3 of t plus theta. And then you apply cosine trig properties, and you simplify it based on the expressions. And then ultimately, when you get to the third to last step, we have the crossed out part, cosine 2 pi plus 3s plus t plus 2 theta, that simplifies to 0. And we end up getting our autocovariance function, which is 1/2 of cosine 2 pi plus 200 tau, which is s minus t, which is a representation of the change between both.
Yeah, so just to elaborate on that a little bit, we can pull this out so easily because this is a constant with respect to random variables. The theta canceled out over here, so we can just pull that out really easily. All right, and as we can see, once again, we have a stationary function with a constant mean function of 0 and the autocovariance function, which we found in the last slide.
All right. Continuing off that, with our discussion, we have the same thing as before. We have the PSD is equal to the Fourier transform of the autocorrelation function. And an autocorrelation function is an autocovariance function, which we found before. And basically, we just take the Fourier transform of r of x of t. So the Fourier transform of 1/2 cosine 2 pi times 300t ends up becoming 1/2 of delta function, f minus 200 and f plus 300. And we got these from the appendix C and D tables of the transforms. And that simplifies to 1/4 times delta functions of f minus 3 plus delta f plus 300 for all of this. And then if we continue on the next slide, we'll have a visual representation of the PSD, where it's basically just having two delta functions from minus 200 and plus 300 up to a quarter. And it's a very straightforward representation, and we've definitely seen things like this before in our EE classes.
All right, so now we're going to apply that process to an LTI filter, as we found is stationary. And here is our LTI filter, our impulse response and its frequency response. A redefinition of the things we stated earlier in the presentation. All right.
And then to continue off this problem, in order to figure out the PSD for this new output, we have to do the magnitude squared times the original PSD. So based on what we have before, we have 2 over 1 minus j 2 pi f, and multiplied by its conjugate, or multiplied by the both conjugate and the regular will multiply together, and we get 4 over 1 minus 2 pi f squared. And then all we have to do is multiply that times our x of x, which we found before, the original PSD, and we have this bottom final answer, which we have for the output, which is 1 over 1 minus 2 pi f squared times delta f minus 200 plus delta f plus 300.
All right. Thank you.
Thank you for watching, and that was our presentation. Hope you enjoyed it.